Alright, let's get started with today's problem. The first problem of the day is going to be LeetCode number 560, subarray sum equals k. Given an array of integers nums and an integer k, return the total number of subarrays whose sum equals to k. Subarray is a non-contiguous, non-empty sequence of elements within an array. Okay. So I guess the first thing that comes to my mind is maybe a sliding window approach. Given that nums dot size is less than or equal to 2 times 10 to the 4, I imagine that this will be an O of n log n or O of n solution. If O of n log n, we could potentially utilize sorting to maybe gain some advantage. Otherwise, we'd just be using a sliding window. Let me think about this some more. So the naive solution is to check all subarrays to see if they equal the amount or if they equal k. This would take O of n squared time to check all subarrays and would be way too slow for an input size of 2 times 10 to the 4. So that's probably not the solution. Generally, if we need to check all subarrays, then a sliding window solution can be a potential vector of help there, right? So if checking all subarrays is too slow, sliding window can help. The idea is that we know the middle amount will not change, only that we will add the right side and subtract the left side. So in that case, maybe a sliding window solution would be start with a subarray of size 1, while the running sum is less than k, increase the array by, or move the right side over and increase window size. So the idea is that while we're less, we just incorporate the next element. If the sum is equal to k after expansion, increment the number of valid windows and slide over the entire window. So for example, for this one, when we go start with 1, we go to 1, 1, that's equal to 2. We'll take that as valid, and then we'll move over and slide over by 1. If the sum is less than k, then, is greater than k, then shrink the window by incrementing the left side and subtracting that value. And then the idea is that this is all incorporated while the right hand side is not at the end. And then so we basically grow to the try to make a proper array size, try to make a proper array length, and then we shrink all the way down from the left hand side if we go over, or we keep it and we slide over if we need to. This will run in O of n time, O of 1 space, because we don't need to store any auxiliary data. Let's see, if the sum is greater than k, shrink the window. I guess my sort of issue with a lot of these sliding windows problems is that they are kind of intuitive, but at the same time it's difficult for me to necessarily think about it in terms of Will this cover all cases? Well, if there's a large, or if there's a value that equals k somewhere around here, right? We will grow to it because our current value is less. Assuming our current value is less, then we will grow to it. Then we will shrink from our left-hand side until we incorporate it. Then we will slide over by 1. So that includes it. If there is a row of sums that adds up to k, we will also include it because we will continue to grow until we hit that mark. And I think that works. So let's see. Are there any other issues that we need to deal with? No, the minimum length of the array is 1. The values inside don't matter. We can think about whether or not we need to... Do we need to do something to account for negative values? Because the numbers that are inside can contain up to negative 1,000 and positive 1,000. Let's see. If we had... Let's say that we had an array that was like, I don't know, like 1, -1, 1, 1, 2, with k is equal to 2. We would start with this 1 down to 0. We can't do anything about that. Increase to 1 again. Also, since it's a subarray, can't do this subarrays. We don't want to sort. We grow, so we start at 1, shrink to 0, grow to 1, grow to 2, 2 works, we slide over. Now we're at 2, 3, 4, 3, so we shrink, and shrink down to 2, and we grab the second one. But we do miss, in this case we do miss, because we do this. We increase it so that we go to here. Then when we slide over, we incorporate the 2, but in reality we kind of miss the other, the 1, 1 in the middle. So perhaps what we want to do actually, instead of sliding over the entire window, is just if it's greater than or equal to k, we just shrink the window, and then that's how we sort of slide over. So we increase, 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 increase. Here we hit the value k equal to. Here we decrease. Okay. No, but it doesn't work because we still have this negative here, right? So now this is still technically less than 2. So now we grow to this value. And then we grow to this 2. And then we start shrinking. So that doesn't really work. How else could we do this? The main crux of this is that we deal with a negative value that we can't really move around. Because this negative value then basically ensures that we cannot, or there's no guarantee that by increasing the value and then shrinking it that we will actually get to the optimal value. Let me think. Because by having this 1 here, if this was just a regular 1, then we would get here and then we could shrink into this 1 and then slide over and then increment, and that would be fine. Problem then really is that we have this negative value here. Maybe if we have a negative number on the left-hand side, then shrink the window instead before growing. The idea is that, okay, we go here, we grab this, okay, that's fine. Then we move, then we shrink it by 1 to get to the next possible subarray. Okay, so this is less than the value, but the head is a negative value, so we shrink by 1 again. Okay, we got this number. Now we shrink again. Okay, this is less. We increment. Okay, we grow. This is over, and then we shrink again. So the idea is that if there's a negative number on our left-hand side, then by shrinking the window on that side, we will actually grow our sliding window sum, even though really we're shrinking our sliding window. So maybe that's the solution there. Still a little bit iffy in terms of the values. I wish they gave me more examples in terms of using negative numbers, because it's a little bit tricky, I think, to... Maybe this is just one of my weaknesses, but it's really difficult to think of like proper proper test cases. If I did this, I'd start with u, which is not correct. U, that'd be 3. And 2, that doesn't work. Value here starts at 1. Negative 3, that doesn't work. Is there any situation where you'd want to incorporate the negative value? Yeah, I mean, if we had a 4 here, right? Then this would be valid, and we want to incorporate that. The problem is that we do have a valid subarray here, which is the 1 and 2. But it's kind of being blocked by this 1 and 3, right? 1 and negative 3 here, right? Because here, okay, we do this. It's not. We grab the next one, and that's negative 3. Okay, whatever. So now we're at negative 2, negative 1, 0, and then 2. But we have a negative number in our midst, so maybe rather than if we have a negative number on our left-hand side or in the window at all, then we shrink the window until shrink the window instead before growing until that negative number is gone. But that really also depends on whether or not because we could potentially have a negative number that actually benefits us, right? Maybe there's a property we can use. We can't say for sure that if we encounter a 1 and then a negative 3, that this is not part of a solution, because again, if we had something like negative 1, 3, and 4, then this is of course a solution. Sorry, 5. This was a 5, yeah. But we don't know for sure as we're expanding the sliding window. Like we go 1, negative 3, okay. But this negative 3 could be potentially part of a solution, right? So we want to keep on growing until... kind of want to keep on growing until we can't grow anymore. And then we start shrinking. Well, the right hand side is not the end, and the left hand side is less than right, maybe, then the idea is that, okay, we grow to here, we grow to here, and let's say that this is a 1 again. We grow 1 into -3, so that's -2, -1, 0, 2. Okay, that doesn't work. However, we have a negative number in our midst, so we shrink here. Still have a negative number. We grow once. So the idea is that we start here. We grow until the end because the right hand side is less than the end. So we just increase. Okay, so now we have a negative number. So now we decrement, or now we shrink the left hand side. Then it's still here. So right hand is at the end, but left is still less than right. So we increment or decrement again, left hand side. Okay, now we're at the over amount. And then now we continue to decrement normally. Okay, so maybe we don't care about the right hand side being at the end. We just care more about the left hand side being less than right. And then here, while the running sum is less than k and right hand side is less than size, because we don't want to increment, or we don't want to grab something that's out of bounds for our array. Okay, wonder if that would work. So we just keep on growing while it's less until we can't anymore, and then we start shrinking once. Next step, left hand side still less than right. We can't grow anymore and we're still less, so we shrink again because there's a negative number. Maybe then the solution is actually much simpler and we just say shrink the left hand side, and also if the window equals k increment value, and then shrink the left hand side no matter what. So we go here, we grow until we can't anymore, or until we go over. And then we stop here, and then it's not equal to k, and then we shrink, not equals to k, shrink, not equals to k, shrink, equals to k, increment, shrink, not equals to k, and now they're equal, so it doesn't matter. Less than or equal to. This might work. We'll give it a shot, and we'll see if it works. Because I don't really think I have many other ideas at the moment. I think the main issue is just, again, that the negative numbers, I think, kind of throw a wrench in the works, because there's no guarantee that by shrinking the left-hand side we'll get a smaller number. We might actually get a larger number. But to that extent, maybe it's okay to just keep on shrinking the left-hand side no matter what. Because let's say that there exists a negative number within the window, and our value is greater. Then by shrinking, let's say that we get rid of it, and now our value is greater. Well, then there may be, at that point then, an existing subarray within that window which has the amount k equal to k. And say that it wasn't the case, that by getting rid of the negative, or let's say that our value is, let me think, if our value is less and we remove that, that's like the pretty obvious case. Like we increase our value, right? But I think the logic is somewhat sound in the sense that if we have a larger amount, or if we're over the amount that we need and we remove a negative number in that sense, then even though we do have a larger sum now, we know that we can't possibly have that negative number be part of our subarray. Otherwise, it would have been part of it already. Right? Otherwise, it would have fit within the sum. Yes, because it would have grown into it. I think. I could be wrong in there. Well, we'll think about it a little bit more and we'll submit it and we'll see if there are any other edge cases that we need to worry about. Maybe I'm wrong. Maybe this isn't even a sliding window problem, but subarrays usually tend to be that. And we can't necessarily do backtracking because that's a little bit too slow. And we don't need the number. We don't need each individual subarray. We just need the number of subarrays. I'm just thinking if n squared would work with maybe like a dynamic programming approach, where we say, okay, we start at each one, and then we say if we can create a subarray of size blank at this value. What does shrinking on the left side actually do for us? We'll get started with the coding and we'll see where we end up. So, var left is 0, var right is equal to nums at 0. And if nums.size is equal to 0, return if nums at 0 is equal to k, then 1, else 0. Idea is that if there's one value within our numbers array, then there can only be one combination. Let's see. Now I'm thinking whether or not we could do a greedy approach by saying like, okay, at this number we can say if it's the same as k, then we just we do that, and then we continue. The next step, if it's less than, no, but we still need to shrink the backside. Okay, yeah, no, I think we're fine as we are. I think we're fine. We can say while left is less than or equal to right. And say var running sum is equal to 0, or rather nums at 0. And then we can say it contains negative number, starts at false. So while our running sum is less than k, and we can do right is less than num size first. Right is equal to, or running sum plus equals nums at plus plus right. If nums at right is equal to or is less than 0, then contains negative number is equal to true. Actually, this contains negative number, it doesn't matter. Then afterwards, while the right is less than that and our running sum is less than k, then we grow, and then we say if running sum is equal to k, then var subarrays starts at 0, subarrays plus plus, and then we do left plus plus. Well, we can do running sum minus equals nums at plus left plus plus. We want to remove our current value from our left and then increment it, and then return subarrays. I didn't spell this the same. Yeah, I didn't, because for some reason I added an additional R there. Let's see. Size minus 1, I guess. Let's see. So this one, 1. Let's see. Left is less than or equal to right. We did this. We started at this 1. Oh. Nums at right. Do that. Nums at 0, that's fine. We increment to here. And then that's fine. And then we reach that amount. And then we increment the number of subarrays. And then we shrink our left side. And now our right side is still here, is still less than our num size minus 1. And then we increment it, right? I'm confused. Maybe this num size minus 1 is interfering. Zero, 0, 1, 1, 2, 2. Not quite what we wanted. Maybe we do it here instead of there. Zero, 1, 1, 2, and then 2, 2. Yeah, makes sense. Let's go ahead and run the test cases for the other ones. I'm really not sure what I changed about it. I guess I changed the left and the right parameters a little bit, but so it seems to work for those test cases, but 1, -1, 1, 1, 2, and 2, and 1, -3, 1, 1, 2, and 3. I think like I did a dry run and that's how I came up with this solution, so it should work, but I don't know. Let's see, 2 and 1 and 3 and 1. Okay, so we didn't get the answer here that we wanted. So let's focus on this one, and then let's also do a print line left, right. So it should be here, here, then we get to here, and then 2. then we shrink once, then now we're less, so we need to grow again. But then we miss that amount. Okay. Hmm. But we don't always want to throw away a negative number, because that negative number could be useful to us. I feel like we got close, but there's some part that just didn't quite work out. In any case, it's 30 minutes in, so let's take a look at the solution and let's see how close we actually got. Okay, so this solution is actually very, very smart and reminds me of the previous problem. Which one was it? It was, let me check. I have to check back at my notes. Contiguous array. Because we're using a hash map rather than a sliding window. I think these comments are really good. These comments explaining like sort of, okay, if a sliding window or if the array has a numerical value of negatives, then a sliding window likely won't work. I think that seems to be a pattern that holds generally. So pretty good on that point, and something that I will need to remember as I continue working through these problems. Anyways, let's get to talking about the solution at a high level. And I think this comment here really helped me solidify my understanding. So huge shout out to this person over here. So let's start off with the theory behind it. So say we had any arbitrary subarray. We know that if we sum up all the numbers at the end, from the beginning to the end of this given subarray, that the sum that we have at the end will be the sum that we had at the beginning before we started counting numbers within the subarray, plus the sum of whatever is in the array, right? So whatever we started with plus whatever's inside the subarray will be what we end with. I think that's pretty straightforward. Now, in this particular problem, we want to target the value k. So we should set our equation now to say that whatever we start with and whatever we end with, we want our middle part to equal k. So that's this part right here, so that our sum end is equal to whatever we start with plus k. Now, when we search through our array, we will always be keeping track of our sum end, right? Because we're just going to be continuously updating our running sum. And what that means is that we are going to be, rather than searching through each individual sum end or sum begin for k, for a difference in k, what we'll do is that we'll actually put it into a hash map instead, so that we don't need to search through all the previous arrays. And instead we basically say that, okay, if we have an instance where we started with some amount that is equal to our end minus k, then we know that because we ended with this amount at this point at our current index, and that we started with this certain amount at this index, at some given index previously, that the difference, because of the difference, we know that that subarray exists, and that there is one instance, at least one instance of this subarray. And furthermore, if we have multiple instances of this sub begin, so basically, if let's say that we started with a value here that equals 0, and then we end off with k. Well, if we had a point in our array before that where we go up and down and whatever, right? But we still end up at 0 before. Well, we can create one subarray with one of the zeros that we found. And then we can actually create another subarray where we actually include the other part of the subarray that goes wherever but ends up back at 0 again, right? As long as our sum end is at k. So that's why we, at the bottom here, when we're looking at this solution, we actually add the frequency of the number of times that we've encountered this sum begin because for every instance of sum begin, we can end it and create a new subarray. So that's basically our solution. We create a map where we put instances of our sum begin at that point. Hold on. Sorry about that. So we hash into our map the sum that we currently have, and for each instance following it, we say, okay, is there another instance where we've encountered this sum beginning, where if we subtract what we have currently and what we have at that point, we get k. We kind of do this in a different way where we actually subtract k from our current amount and we say, okay, is there an instance where the beginning part exists, right? That way we can get the step done in O of one time. And we just proceed and go through. If it exists, then we will increase the number of subarrays that we can create by the amount of times that we've actually encountered that old sum begin, because we know that for each instance of that sum begin, every time that has occurred, we can create a new subarray that equals k to that point, starting at whatever point, arbitrary point in the past, until our current point right here where we have our sum end. This runs in linear time and uses linear space because we also need to consider adding in our frequencies, which potentially could include every single, or could create one value for every value within our array if we happen to have all positive numbers or something like that, right? Because then we'll never have an instance where each frequency or each sum begin will be the same. In any case, I hope you learned something. I hope I explained that well enough, at least for you to get sort of like the basic idea. And I will see you for the next problem.